Good morning. Can everyone hear me? So firstly, I would like to thank the organizers for this wonderful conference at ICTS and letting me be a part of it. I'm going to talk about cosmology with HIRAX. This is a work done in collaboration with Warren, who's a master's student at UKZN, and Kavi Moodley. So I'm just going to start off with 21 centimeter intensity mapping. So just to say that 21 centimeter is becoming popular as a cosmological probe. The hydrogen is abundant, so there is not much confusion with from other emission lines. And the frequency observed gives a very good measurement of the redshift using this relation. And we do use 21 centimeter to study the matter and growth of structure in the universe. This slide is just for completion, because I'm pretty sure everyone knows what BAOs are. HIRAX is actually trying to measure BAOs, which are just the oscillations in the primordial plasma, which can be seen in the CMB anisotropies as well as the galaxy correlation function. The BAO scale at 150 megaparsec is used as a standard ruler to probe the geometric measure and expansion history. And at late times, it is used to study dark energy constraints also, so of between redshift 0.8 and 2.5. So Teeth already gave a very nice introduction to intensity mapping. So for BAO measurements also, since we need a large volume, intensity mapping becomes very popular for it. Since if you are measuring individual galaxies, the H1 in the H1 21 centimeter line in individual galaxies is very weak. So instead, what we do is we stack up the signal from different redshift bins. So we get a low resolution survey at the cost, but what we get is a large volume in a small amount of time. So it is quite like the CMB, but here we are getting a 3D map of the H1 density at the cost of resolution to the galaxy scales. And since we retain the high frequency information, we can get the redshift information also from them. I won't go in much details about the foregrounds, but the thing is, even though the foregrounds are about 4 to 5 orders of magnitude higher than the H1 signal, since it's much more smoother compared to the H1, which has more structure, it can be possible to filter them out. So this is from the line intensity mapping report from 2017, giving a list of all the major intensity mapping experiments. Some of them are H1, some of them are CO, so on. Some of them are single dish, some of them are interferometers. So I'll talk about HIRAX, which is located in South Africa in the Karoo Desert. So once it is completed, it is supposed to be 1,024 6-meter stationary dishes. It will cover a survey area of 15,000 degrees square. It will run for about 4 years. And the primary aim is, as I mentioned, it's to measure the BAOs and to try to constrain dark energy. There are other secondary goals like looking at FRBs and pulsars, and John Sievers is giving a talk later today. Since we are interested in the dark energy constraints, we are looking at these kind of redshifts, and so the frequency we're interested in is 400 to 800 megahertz. We've got like 1,024 channels also. And if you search on Google, the first thing probably you will get when you search for HIRAX is a thrash metal band from California. But believe me, its actual acronym was inspired from a badger-like animal called rock HIRAX or DASI, which can be aggressive also. Okay, so where are we located? So I'm based at Durban on the east coast of South Africa. This is Cape Town. So the SKA site, Clairefontaine, where Meerkat, the SKA precursor, as well as Seabass is located. HIRAX site is about 100, 200 kilometers away from the SKA site, which is, this is also a very radio quiet zone. So that's at Losberg. We have grants to carry on making 128 dishes, and maybe John will tell you more about it. Currently, what we have is a prototype of 8-element prototype at Khatri, which is about 50 kilometers from Joburg. It's a wonderful facility which has a wonderful staff who has helped us to put up this 8 dishes. Right. So HIRAX is quite similar to its northern counterpart, CHIME, the Canadian Hydrogen Intensity Mapping Experiment. There are a few differences. One of the advantages of HIRAX is the southern hemisphere location, and it makes it easier to do cross-correlation studies with CMB observations, which are more located in the southern hemisphere, as well as some optical experiments like DES, LSST, and so on. And also, since the center of Milky Way, you can see more of it in the southern hemisphere, we hope that there'll be more pulsar observations in the southern hemisphere. Probably I'll skip this, but this is just to show you some of the forecasts with HIRAX 128 element array and 1024 element array, just showing you that it can do well to constrain the BAOs as well as the dark energy parameters. So one thing which I'm interested in, because I come from a CMB background, is the way the analysis is done for the data. So there's something called the M-mode analysis, which is done mostly for a drift scan interferometer. And these are the two references. So what you have is the data, the visibility. You write in terms of this simple linear equation, where B is the beam transformation matrix, kind of like the Poynting matrix, which takes into account the instrument and the sky rotation. And ALMs are like the spherical harmonic coefficients. And what the interesting thing is, once you write it in terms of the M modes, for each M mode, what happens is it becomes independent. And for HIRAX, this B matrix can be quite big because it depends on the number of baselines, the number of bands, and so on. But you can split it into subbands, and you can analyze them separately. And also the M mode can be, you can parallelize and put them running in different nodes on your cluster. The other interesting thing about the M mode analysis is analyzing the foregrounds. So you can actually downgrade the foreground dominated modes using something known as the KL transform, KL filter. And this is also used, this has also been used in CMB in EB separation, CMB polarization. So I'll give you, the next few slides are something which I'm working on. It's cross-correlating HIRAX with one of the Southern Hemisphere experiments, LSST. So what you see here is the LSST coverage. And we just have the HIRAX logo here because I didn't have the overlap properly. So why are we interested in doing the cross-correlations? So the case for radio-optical cross-correlation is more historical because the first detection of the 21 centimeter signal was done with GBT and WiggleZ in this paper. We have the constraints for omega H1 as this. And cross-correlation also does help in many other ways. So you can do complementary physical constraints. You can do cross-confirmation of results. And for our case, we have a mutual support in terms of redshift, because LSST will provide photometric redshifts for the continuum survey, whereas HIRAX, using H1 intensity mapping, can calibrate the LSST photo Z using this cross-correlation method. There's also other things, like you can remove the systematics when you're doing these kind of cross-correlations, and many other groups are studying cross-correlations of 21 centimeter and galaxy surveys for different purposes. So these are just the H1 autocorrelations. So this is just the temperature fluctuations of the 21 centimeter. In terms of the mean 21 centimeter, the H1 bias, and the redshift space distortion term. And you have this is the noise, which also depends on the system temperature of the instrument. And this N is just a baseline density, which tells you, which is different for different arrays. It will be different for HIRAX and CHIME. So this is what is plotted here, the power and the noise. And this is just the signal to noise. So one thing just to note from this is the autocorrelation, the H1 autocorrelation is about 800 at L of 2000 for any of the bins, redshift bins. The same for galaxy autocorrelations. You can see the noise term is just the short noise. And similarly for the signal to noise, you can get about 800 at L of 2000. But when we look at the H1 galaxy cross power spectrum, so this is a signal on the noise, but when you look at the signal to noise, you can see that there is a massive drop in the SNR. It was about 800, between 700 and 800 for L of 2000. It actually comes down to about 100. And the reason is because of the galaxy kernel. When you plot the galaxy kernel in Fourier space, you've got the k perpendicular and k parallel modes. You can transform them to observational Fourier coordinates L and Y, and you can see that it falls off very sharply with k parallel. And you can see that in the SNR plots also. You can see that the power almost falls off with Y. Right? The next challenge is from foregrounds. So as I said already, the foregrounds are 4 to 5 times higher than the 21 centimeter signal, but they actually contaminate the large-scale frequency modes, which correspond to the small k parallel modes. And because of the wedge effect, the dominant effect of foreground removal is such that we become insensitive to power at low k parallel modes. So in our analysis, what we have done is we have tried to avoid the modes k parallel less than 0.01. If you take that into account, what happens is the signal to noise falls further. So we initially had 100. After we account for the foreground removal, it falls to 10. Now, there is a way to improve this. So what we have done, the binning system we have done is, since HIRAX has a frequency range from 400 to 800, the bins are for a frequency bin of 100 megahertz, which corresponds to delta Z about 0.3. If we choose an optimum redshift bin, so in this case, I've chosen delta Z to be 0.1, the signal to noise can be slightly improved. So instead of 10, we have something around 25. This is mainly because if you have a larger redshift bin, the smearing effect can actually cancel some of the signal. So if you have a narrow bin, it can improve slightly. There is another way to get a little higher signal to noise in the cross correlations. That is by using the bispectrum instead of the 2-point correlation power spectrum. So this is something which I'm currently doing, but this has already been done for CMB lensing and 21 centimeter cross correlations. So the concept which is used here is you have 2 small scale 21 centimeter modes, and you have a long wavelength large scale mode. So what happens is this density modulation, which can enhance the small scale modes. And this is what happens. So if you have a good overlap of the 2 kernels, what happens is when you do the power spectrum, you can see that with k parallel, with increasing k parallel, the power goes down in the power spectrum, whereas in the bispectrum, the power is, the SNR is actually quite high compared to the power spectrum. So just a final result. So when we do the bispectrum analysis, so you can see that the blue contours are from the 21 centimeter autocorrelations. If you include the bright spectrum, in certain cases, it breaks degeneracies and you can get a better constraint. But when you combine both of them, so when you have 21 centimeter auto plus the bispectrum constraints, this is, mind you, it's all for lensing and H1. So what you get is the green contours, which are definitely doing much better than either of them. Currently, we are also working on the same concept for the Galaxy H1 bispectrum. And so here is my summary and status. So as I said before, like intensity mapping is a robust way to test cosmological parameters. And in the cross power spectrum, we have a significant loss of SNR because the galaxy kernel falls off very sharply. And because of the foregrounds, we get a further loss of SNR, which actually doesn't come as badly in the autocorrelation, but it comes more in the cross correlation. We can choose our redshift bin wisely to get a slight improvement, but also looking at the bispectrum might help. And HIRAX is currently funded for 128 elements to be built in the Karoo Desert. So the building is going to start in early 2019. Thanks for your attention.
Impressed by how much the bispectrum is improving, which is different from galaxy clustering. When demonstrating that bispectrum improves is not straightforward. Questions?
So one of the reasons you said the signal to noise is going down because the kernel along the line of sight. So is it possible to look at 3D power spectrum given you have actually intensity mapping, and so you can map it to redshift and measure 3D power spectrum rather than CL, which will reduce the smearing a lot and help you improve.
So for my case, because, okay, I'm pretty sure if you are doing for the lensing case, it is possible. The thing is, since I'm looking at LSST and H1, so I'm actually, the main aim was to look at photo-Z calibrations. So that's why I was plotting on CLs. But you do see, even if you plot P of K, like P21 also, the 3D power spectrum, you can see that there is a decrease in SNR. So is that what you're asking? Whether you see the same if you do it in power spectrum?
Yeah, so you see the decrease even when you do 3D power spectrum, like in place of CL?
Instead of CL.
Right.
Yes. When you plot the SNR, it's still lower.
I see.
Yeah.
More questions? Okay, if not, let's thank the speaker again.